Hi, welcome to this walkthrough and explanations on the OCR A A-Level Chemistry Paper 3 of June 2018. This paper is called Unified Chemistry and it is designed to test candidates on the entire chemistry course. There are no MCQs in this question paper and there are only short or long answer questions. The total marks for the paper is 70 and the time allotted is 1 hour 30 minutes. So let's get on with the questions. Question 1. This question refers to the elements in the first three periods, hydrogen to argon, of the periodic table. Select an element from the first three periods that fits each of the following descriptions. The element that forms a 1- ion with the same electron configuration as helium. You know, helium has got an electron configuration of 1s2. Therefore, if there is an element which achieves this configuration after taking on an extra electron, that is 1- charge here, then that must be an element which has got one less electron than helium, that is hydrogen. Hydrogen has got 1s1, therefore if it takes on one more electron it will become 1s2. So we need to write here hydrogen. Part 2. The element with the highest first ionization energy. So if you look at the trends in first ionization energy, if you go across the periodic table, the first ionization energy will increase, and down a group the first ionization energy will decrease. There are a few reasons for this. Across the period the number of protons increases and therefore there will be an increased pull, that is a positive charge pulling the electron towards the nucleus. Secondly, there is no additional shielding when you go across the period. Thirdly, when you go across a period, the atomic radius decreases due to increased pull by more number of protons, and this also increases the energy required to separate the first electron. And due to these reasons, the element which is at the topmost and the rightmost part of the periodic table will be having the highest first ionization energy, and that is helium. Part 3. The element in period 3 which has the successive ionization energies is shown below. So the ionization number as well as the ionization energies are given. Here you can see the difference in ionization energy increases as you try to remove electrons one after the other. But after the second electron, the third requires a much bigger quantum of energy, which suggests that in the outermost shell of this particular element, it has got 2 electrons. So here the difference is 600 kJ. Here the difference is 6300 kJ. And here the difference is 2800 kJ. This means that after the second electron, the third electron in the atom of this element is in the next previous shell, requiring a much bigger quantum of energy to remove it. This suggests that in the outermost shell of this particular element, it has 2 electrons, and as it is in period 3, it must be magnesium. Part 4. The element which forms a compound with fluorine that has octahedral molecules. An octahedral molecule is one in which there are 6 bonding pairs of electrons and 0 lone pair of electrons. So it must be sulfur, because sulfur is in group 6 and it has got 6 valence electrons with which it forms 6 bonding pairs with fluorine in this shape, which is octahedral, with 0 lone pairs. Part 5. An element which reacts with water to form an acidic solution. It must be chlorine or fluorine. Watch out, there are other elements in the first 3 periods which will react with water to form alkaline solutions, but we are talking about acidic solution here. Part 6. The element X which forms a compound with hydrogen XH3 with a molar mass of 34.0 G per mole. This is quite easy. Now just take out 3 from 34, it's 31, and look in the periodic table which element has got atomic mass 31, and it is phosphorus. 7. An element which forms a compound with hydrogen in which the element has an oxidation number of -4. So it must be a compound which is XH4. So that element must be carbon. Part 8. The element which has a density of 1.33 times 10 to the power of -3 grams per cubic centimeter at room temperature and pressure. Now this density is very small. We can write this as 0.00133 G per cubic centimeter. In comparison, water has got a density of 1 gram per cubic centimeter. So this must be a gas. Okay, if it is a gas, 1 mole of this gas at room temperature and pressure must be having a volume of 24 liters. So we can say 1 mole is having a volume of 24 liters, which is equal to 24,000 cubic centimeters. Therefore, molecular mass is equal to mass of 1 mole, right? Therefore, that is equal to 0.00133 times 24,000 cubic centimeters, which when I put into calculator I get 31.9. So we can write this as grams per mole because it must be the molecular mass, right? Looking into the periodic table, which element has got this atomic mass? Now don't go for sulfur because sulfur cannot be having this low density. Sulfur is a solid. It must be having a density much higher than even that of water. Therefore, it must be a gas, and a gas having this molecular mass must be a diatomic molecule of the gas. So oxygen is 16, therefore O2 is 32. So this must be O2. Part B. Table shows some properties of period 3 chlorides. Group 1, 2, 4, 5 and 6 chlorides names are given. Then electrical conductivity is given in solid state as well as liquid state. Their melting points are also shown. Explain the properties shown in table 1.1 in terms of bonding and structure. One thing that stands out here is both sodium chloride and magnesium chloride have high melting points, and in the liquid state they both are good conductors of electricity. The reason for this is both sodium chloride and magnesium chloride are giant ionic lattices. They can conduct electricity in liquid form as ions are free to move in liquid state. But in solid state, they are poor conductors of electricity because in solid state the ions are not free to move. Also, sodium chloride and magnesium chloride have high melting points because they exist as giant ionic lattices and there are strong electrostatic forces of attraction between the ions. In contrast, SiCl4, PCl3 and SCl2 are simple molecules. They have only weak intermolecular forces of attraction in the form of London forces. Hence, they have comparatively low melting point. They are poor conductors of electricity because they do not have ions to carry the charges. So let us write that out here. NaCl and MgCl2 exist as keywords giant ionic lattices. Hence, their ions have strong electrostatic forces of attraction leading to high melting points. they can conduct electricity in liquid state as ions are free to move carrying charges but in solid state the ions are not free to move, hence they are poor conductors of electricity in solid state. Now we have to write about the simple molecular substances. In contrast, SiCl4, PCl3 and SCl2 are simple molecular substances and they have only weak London forces between molecules. Hence they have a low melting point. They do not have ions to carry charge, hence they are poor conductors of electricity. This question carries 5 marks, so it fully justifies our long answer here. 2. This question looks at reactions of hydrogen peroxide and cobalt-2 ions. Aqueous hydrogen peroxide decomposes as shown in equation 2.1. 2H2O2 aqueous gives 2H2O liquid plus oxygen gaseous. Okay. The reaction is catalyzed by manganese 4 oxide MnO2. A student investigates the decomposition of hydrogen peroxide solution as outlined below. The student adds 50 cubic centimeters of H2O2 aqueous to a conical flask. The student then adds a small spatula measure of MnO2 and quickly connects the flask to a gas syringe. The student measures the volume of oxygen every 200 seconds. A table of results showing different times and volumes of oxygen collected is given. Here is the question. Process the results as outlined below. On page 5, plot a graph of volume of oxygen against time and use your graph to find the rate of the reaction in cubic centimeters per second at t is equal to 500 seconds. Show your working on the graph and in the space below. So let us plot time on the x-axis and volume on the y-axis. So here time in seconds, here volume in cubic centimeters. Okay, so to select the scale, we should have time from 0 to 1400. So let's do 0 here, 200, 400 goes up in 200s, 600, 800, 1000, 1200, 1400. Okay, here we need to have the volume on the y-axis from 0 to 50. So it will be easy if we choose 10 divisions to show 10. So it is easy to plot then. 20, 30, 40 and 50. Cool. Now looking at the table here, here is the first point, 200 in 15, 428, 636, 35, 36, 841, 1046, right, 1248. We have got 2 divisions less of 50. Okay, and then 1400 is 50. Let us join the points now with a smooth curve. Alright, so let me remove the earlier one. Now we have to find the rate of the reaction at t is equal to 500 seconds. That means we have to draw a tangent to the curve at t is equal to 500 seconds. T is equal to 500 is here. Let us show on the graph. Now let us draw a tangent. I have now completed the tangent at t is equal to 500 and also completed a right angle triangle so that we can calculate the gradient. Let's call this point as P2, which will be having x2, y2 as coordinates, and this point as P1, which has got x1, y1 as coordinates. Now gradient will be delta y over delta x, that is y2 minus y1 divided by x2 minus x1. So let's look at the y2 coordinate here. It is 52. So we can say gradient is equal to, let's go back to the space in the question here. So gradient is equal to y2 minus y1 over x2 minus x1 is equal to 52. Take away. This is 15 or 16. I think it is 16. So 52 take away 16 divided by the x coordinate of this point is 1000 and the x coordinate of this point is 100. So this is 1000 take away 100, 36 over 900, and putting that into the calculator we get 0.04 cubic centimeters per second. We can explain that this is the rate of reaction at t is equal to 500 seconds. Next part of the same question, the student allows the reaction in equation 2.1 to proceed until no more gas is evolved. The volume of oxygen in the syringe is now 55 cubic centimeters measured at RTP. Calculate the initial concentration of the H2O2. Give your answer to two significant figures. Let us first write the equation here. from the question, 2H2O2 aqueous decomposes to 2H2O liquid plus O2 gaseous. Let us also document what we already know. Here it is 50 cubic centimeters volume, and we know that this is also 55 centimeter cubed volume. From here, our strategy would be to calculate the number of moles of oxygen formed, and from there calculate the number of moles of H2O2 using this equation, and from there calculate the number of moles of H2O2 in 1 liter, which is its concentration. Remember that 1 mole of any gas at room temperature and pressure will occupy 24 liters. So number of moles of oxygen in 55 cubic centimeters will be 55 divided by 24 liters, which is 24,000 cubic centimeters, which is equal to 2.2916 times 10 to the power of minus 3. From this stoichiometric equation, we see that 2 moles of H2O2 will produce 1 mole of oxygen. Therefore, if these many moles of oxygen are formed, then the number of H2O2 moles will be 2 times of this, 2.2916 times 10 to the power of minus 3 times 2. Putting it to the calculator, we get 0.0045833. This is in 50 cubic centimeters of H2O2. Therefore, concentration of H2O2 is equal to number of H2O2 in 1 dm cubed. That's equal to, you multiply this by 20, 0.0045833 times 20 to make it 1000 cubic centimeters, and that is 0.092 moles per dm cubed. Part B. Hydrogen peroxide can act as an oxidizing agent or as a reducing agent. Some standard electrode potentials are shown below. Use this information to write an equation for a reaction in which hydrogen peroxide acts as a reducing agent. So the key word here is hydrogen peroxide acts as a reducing agent, which means it should get oxidized. So let's write it gets oxidized. Therefore, among these 4 systems here, look for a reaction in which H2O2 gets oxidized. So you can see here H2O2 on one side and plus 2 electrons on the other side, which means H2O2 is giving away electrons here. Therefore, this is a reaction in which H2O2 gets oxidized. But it's written in a form in which the reaction is a reduction reaction. So we need to reverse this and write it as H2O2 aqueous gives 2H positive aqueous plus O2 gaseous plus 2 electrons. Now this is written as an oxidation reaction. Now we should look for another reaction in which a species gets reduced by H2O2, also taking into account the relative electrode potentials. The electrode potential for this first reaction that we noticed here is 0.68 positive. Therefore, the other reaction must be the one in which the electrode potential is more positive than this, because this has to be more negative or less positive, so the other one must be more positive. So looking into the other reactions, the second reaction cannot be, because here H2O2 is getting reduced. So let's cross this out. That's not our required reaction. And the third one could be, but the electrode potential is 0.34 volts only. So it will not pair with H2O2. Hence, this also we can cross out. And then the fourth one fits the bill because it is one in which the electrode potential is 1.51 volts, which is much higher than that of 0.68 volts. The only concern is here we have 2 electrons and here 5 electrons. So in order that these two are balanced, we need to multiply this equation by 5 and this equation by 2 to combine them together. So multiplying this equation by 5, we can write 5 here, we can write 10 here, 5 here, and 10 here. Multiplying this whole equation by 2, we get 2MnO4 minus aqueous plus 16H positive aqueous plus 10 electrons gives 2Mn2 positive aqueous plus 8H2O liquid. Adding these two equations together, we get the overall equation. So 5H2O2 plus 2MnO4 minus plus 16H positive plus 10E minus gives 10H positive plus 5O2 plus 10 electrons plus 2Mn2 positive plus H2O, 8 of them. Cancelling terms which are the same on both sides, this and this go, and then we have got 16H positive here and 10H positive here, so we can cancel this 10H positive here and write this as just 6. Okay, and then combining them together, we got the overall. So 5H2O2 plus 2MnO4 minus gives, oh, we got the 6 positive H here, H6H positive here, gives 5O2 plus 2Mn2 positive plus 8H2O. You can see that H2O2 works as a reducing agent here because in MnO4 minus, manganese has got an oxidation state of +7 and it gets reduced to +2. Therefore, that's a reduction reaction there where H2O2 reduces it. And MnO4, you can say, oxidizes H2O2. Also, when you write the overall reaction, there is no need to write this reversible reaction. You just write this as a forward reaction. Part C. Cobalt-2 forms complex ions with water ligands and with chloride ligands. With water ligands, cobalt-2 forms a pink octahedral complex ion COH2O 6 times 2 positive. With chloride ligands, cobalt-2 forms a blue tetrahedral complex ion. A student dissolves cobalt-2 sulfate in water in a boiling tube. A pink solution forms. Experiment 1. The student places the boiling tube in water bath at 100 degrees centigrade. Concentrated hydrochloric acid is added dropwise. The color of the solution changes from pink to blue. Experiment 2. The student places the boiling tube from experiment 1 in an ice water bath at 0 degrees centigrade. The color of the solution now changes from blue to pink. Write the equilibrium equation for the reaction that takes place when the color of the solution changes. The starting point here is cobalt-2 sulfate is dissolved in water. Therefore, the pink solution formed will be, as per this will be COH2O 6 times 2 positive ion. When this is reacted with hydrochloric acid, the color changes from pink to blue. That's what is referred to in the question here, the reaction that takes place when the color of the solution changes. Here we need to know the structure of the compound cobalt forms with chloride ligands. There is a small clue here though, it says tetrahedral complex ion. A tetrahedral shape is when there are 4 bonding pairs and 0 lone pairs. This indicates that there are 4 chloride units in this complex ion. Moreover, when chloride forms ligands, it can only form 4 ligands, not 6, unlike H2O, because chloride ligands are bigger in size. Now this all indicates that the compound formed will be COCl4. And now let us talk about the charge of this ion. Unlike the water molecule here, which is neutral, the chloride ion has a negative charge, one negative charge. So 4 of them will make 4 negative charge. Alright. Now cobalt has got 2 positive charge here as indicated by the earlier ion. When you net this off, you get a 2 minus charge. So that will be the charge of this complex ion. So we can now write the equation starting with CO H2O 6 times 2 positive plus, we need at least 4 chloride, right? So 4Cl minus gives COCl4 with a 2 minus charge there, plus all these water molecules have to be balanced here, so 6H2O. Since this is an equilibrium reaction, we need to show that this is reversible. That's it. Now second part. Explain the observations and predict whether the formation of the blue color is exothermic or endothermic. So in the first reaction, this is the pink solution and this is the blue solution. And we had heated it 200 degrees centigrade. So we can say that at room temperature it was pink solution, then heated, it became blue solution, which when cooled reverted back to pink solution. So what does this indicate? When you heat it, the forward reaction takes place. That means it must be an endothermic reaction. So we could write the explanation here. When temperature was increased, the forward reaction took place. Hence, equilibrium shifted to the right with rise in temperature. So the reaction is endothermic. This question is about ethane dioic acid and ethane dioate ions, COO minus 2 times. The ethane dioate ion shown below can act as a bidentate ligand. Fe3 positive forms a complex ion with 3 ethane dioate ions. The complex ion has 2 optical isomers. Draw the 3D shapes of the 2 optical isomers, and in your diagrams you show the structure of the ethane dioate ligands and any overall charge. Bidentate ligand means each of these ions will attach with Fe3 positive at the center with 2 arms. In the coordinate bond, the ligand provides both electrons to form the linkage, and therefore obviously these 2 oxygen atoms with the lone pair of electrons there as well as the negative charge there will be attaching with the Fe3 ion at the center. Let us now draw the structure as well as the 2 optical isomers. Let this be a vertical line here. Starting from here, let's put Fe at the center, and on the axial positions mark oxygen, oxygen. These oxygen atoms are those with the negative charge in the ethane dioate ion. Now let us draw 4 more ligands here, here, here. We'll complete that later and draw the wedges also. Now put O here, O here. Okay. Now think about the ethane dioate ion. So here, and you have got a line here. Double bond O, double bond O. Similar structures here also. Okay, now convert this into wedges. Darken them. And to complete the 3D format, this will be the dashes. Now this is an ion, so put this in a square bracket. Now we need to calculate the resultant charge on this ion. So for that, think about this. Fe3 positive has got a 3 positive charge, and then ethane dioate ions, each of them has got times 3 is equal to 6 minus. Therefore the overall charge for this ion is 3 minus. Now let us draw the mirror image here, starting with Fe, the axial oxygen atoms, then side oxygen atoms. Okay, that one. And here we should have here, and then we have got one more here as a reflection of this. Okay. 3 minus here. Now change this into wedges. That's it. Let's put the vertical line here to show that it is a mirror image. Part B. It's a long question. Let's read carefully. Ethane dioic acid COOH twice is present in rhubarb leaves. A student carries out a redox titration using aqueous cerium 4 sulfate CeSO4 twice aqueous to determine the percentage by mass of ethane dioic acid in rhubarb leaves. In the titration, Ce4 positive aqueous ions oxidize ethane dioic acid in hot acid conditions. So the reaction is given. Notice here 2 moles here and 1 mole here. That's the proportion. Ce4 positive aqueous ions have a yellow color. Ce3 positive aqueous ions are colorless. The student weighs 82.68 grams of rhubarb leaves and extracts ethane dioic acid from the leaves. The ethane dioic acid is added to dilute sulfuric acid to form a colorless solution which is made up to 250 cubic centimeters with distilled water. The student heats up 25 cubic centimeters of this solution to 70 degrees centigrade and titrates this volume with 0.05 moles per dm cubed CeSO4 twice from the burette. The student repeats the titration to obtain concordant/consistent titers. So the table is given. This titration is self-indicating and the student does not need to add an indicator. What color change would the student observe at the end point? Color changes from dash to dash. In such questions on color changes at end point, always think about what is there in the burette. Okay, let's draw a small sketch to make it clear. Okay, so we have got a conical flask here. Okay, there is one solution here and there is one solution from the burette. Okay. Now think about, in this case, what was the solution taken in the burette? Looking back into the question, I remember I underlined it. Yes, see, with the CeSO4 twice from the burette. So let's write, this is Ce, 4 positive ions in the burette, and the conical flask contains ethane dioic acid. This is yellow color in the burette and this is colorless in the flask. The product of this titration reaction is also colorless, that is Ce3 positive, which is going to be in the flask after the oxidation. That's also colorless. Therefore, during the titration, this flask will continue to be colorless. At the end point, the entire COOH twice, the ethane dioic acid, is oxidized and the next drop from the burette will make this yellow. So the color change at end point will be from colorless to yellow. Part 2. Calculate the percentage by mass of ethane dioic acid in the rhubarb leaves. Give your answer to an appropriate number of significant figures. Firstly, let us calculate the titer volume. So, titer values are final reading minus the initial reading. So this is 25, 23.25, and this is 23.50. Okay, and the last one is 23.15. Okay, now we can see that this is out of question because it's different from the others by more than 0.1. Therefore, the concordant results are this and this. So let's write mean titer is equal to 23.25 and 23.15 division 2, which gives, this is 0.40, therefore 23.20 ml cm cubed. Next, let us rewrite the equation so that we can write all the details underneath. So 2Ce 4 positive plus COOH twice aqueous here and here give 2Ce 3 positive plus 2CO2 gaseous plus 2H positive aqueous. Okay. Now underneath each of them, let us write what we know. So we know that the volume required was 23.20 ml, right? And then it had a concentration of 0.05 moles per cm cube per dm cubed. COOH twice, we know it came from 82.68 grams of the leaves and then converted into 250 cm cubed solution, and then from there we took just 25 cubic centimeters for the titration. Alright, now the products are not relevant here. Let us first calculate the number of moles of CeSO4 twice required in the titration. That is equal to number of moles times the volume is equal to 0.05 times in dm cubed it is 0.0232, and that gives us from the calculator 1.16 times 10 to the power of minus 3 moles. Okay, so as per this equation of the reaction, every 2 moles of cerium 4 positive will react with 1 mole of COOH twice, which means the number of COOH twice moles will be equal to half of this, 0.5 times 1.16 times 10 to the power of minus 3 moles. Okay, so this is in 25 cubic centimeters. Therefore, N of COOH twice in 250 ml, let me write cm cubed, is equal to 10 times of this, that is 10 times 0.5 times 1.16 times 10 to the power of minus 3 moles. That's equal to 5.80 times 10 to the power of minus 3 moles. Therefore, mass of ethane dioic acid is equal to number of moles times its MR. So 5.80 times 10 to the power of minus 3 times its MR is 12 plus 32 plus H 2 times. That is 90. Okay, that gives us 0.522 G. Lastly, therefore, percentage by mass of ethane dioic acid in rhubarb leaves is equal to, let's put this mass in the numerator and put 82.68 in the denominator, multiplied by 100 to write it as a percentage, and we get 0.63134 percentage. Writing this in 3 significant figures, 0.631 percentage. Question 4. This question is about 2 compounds used in medicine. Cisplatin PtCl2NH3 twice is a complex of platinum which is used in cancer treatment. What is the oxidation number of platinum in cisplatin? In this complex, PtCl2NH3 twice, NH3 molecule is neutral. Just like water, it doesn't have any charge. But this Cl2 are 2 chloride ligands. Each of them has got a charge of -1. So -1 times 2 is -2. And the overall charge of this is 0. This complex is neutral. Hence, you can deduce that platinum must be +2. Part 2. Cisplatin is prepared in a ligand substitution reaction which takes place in multiple steps. The equation for the final step forming cisplatin is shown below. PtCl3NH3 overall charge minus reacts with one more molecule of NH3 to give you PtCl2NH3 twice plus chloride ion. In the box, outline the mechanism for the formation of cisplatin from PtCl3NH3 minus. Use curly arrows and lone pairs were appropriate. So you can see in the reactant there are 3 chloride ions, 1 NH3 molecule, but after the ligand substitution it becomes 2 chloride ions and two NH3 molecules and one chloride ion is separated. So while showing the mechanism, we should show how one ligand is broken and another ligand is made. So let us show the structure of the reactant first. PT at the center, it has got 3 chloride ions linked to it and one NH3. Now let's make it as a 3D diagram with widgets as well as dashes. Now this complex ion has got a charge of -1. So put square brackets and show the charge. Right. Now one NH3 molecule comes around nearby, and this nitrogen atom in the NH3 molecule has got one lone pair of electrons, which it happily contributes to form a coordinate bond with platinum. Now chloride ions are large in size, therefore there cannot be more than 4 ligands in one complex. So what happens is this ligand breaks, transferring the electrons to chloride ion heterolytically. That means the chlorine here separates, taking away both the bonded electrons to form the chloride ion. After the ligand substitution, the complex becomes neutral as the oxidation positive 2 charge of platinum is completely met by the 2 chloride ions having -1 charge each. That's it. Part B. Paracetamol is a solid organic compound used in tablets as a painkiller. The structure is given here. Name the functional groups present in paracetamol. Fine. Now we know that this is the famous phenolic group. So let's write phenol here. Okay. This part is an amide. Amides are derivatives of carboxylic acid group. See, in a carboxylic acid group, if you replace the OH with ammonia or ammonia derivatives, then what happens is it becomes an amide. So even these hydrogen atoms can also be replaced by other alkyl groups, but the permanent feature of an amide is nitrogen is linked with the carbonyl group. That is the distinct identity. Now another compound is amines. Okay. Amines are derivatives of ammonia, that is NH3. In this NH3, suppose each hydrogen atom is replaced by an alkyl group, then what happens is you get an amine. So for example, you remove this and make it as CH3 here, it's an amine. These hydrogen atoms can also be replaced, then that will become secondary amine, etc. Now that's the distinct feature of amide. So don't forget, if nitrogen is linked with carbonyl group, it's an amide. So what we need to write here is one functional group is phenol, another one is amide. Part 2. A chemist prepares a pure solid sample of paracetamol from 4-nitrophenol in 2 stages. So the first stage is 4-nitrophenol is reacted with some reagent to give an intermediate, which then reacts with ethanoyl chloride, or commonly known as acetyl chloride, to form the paracetamol. Okay. Describe a 2-stage synthesis of 5 grams of pure paracetamol from 4-nitrophenol. The overall percentage yield of paracetamol from 4-nitrophenol is 40%. In your answer, include the mass of 4-nitrophenol required, the reagents and the intermediate, and the details of purification of paracetamol. So looking at stage 2, the end product is obtained from the reaction of the intermediate, which CH3COCl. Therefore CH3CO is coming from the CH3COCl, and the Cl atom must have gone away with the hydrogen atom, leaving behind the NH group. Therefore the intermediate must be having NH2 there. Therefore, in stage 1, the nitro group is converted into the amine group, and therefore it has been reduced. Reduction is best done by an active metal such as tin in presence of concentrated hydrochloric acid. Drawing the structure here, the nitrophenol undergoes reduction in presence of tin and concentrated HCl to give the OH group remains here, nitro group becomes amine group, okay, and then we need to treat this with sodium hydroxide to neutralize the excess hydrochloric acid, and then from there we will be reacting it further with what? CH3COCl to give the final product, which is the paracetamol. Therefore, let's write reagents tin plus concentrated HCl, then NaOH to neutralize the excess HCl. Okay, so that's the reagent. Then we also need to name the intermediate. The name of this intermediate is 1, 2, 3, 4. That is 4 amino phenol. Now we need to calculate the mass of 4-nitrophenol required for the reaction. Let us put a side heading, mass of nitrophenol required. So starting with, we look at what is the end product. We need 5 grams of paracetamol. Therefore, N paracetamol, this number of moles of paracetamol, will be equal to 5 grams divided by its MR. So calculating the MR from the formula, we get 151, that is equal to 0.03311. If you want to look at the MR of paracetamol, it is 17 plus 12 times 6 plus 4 hydrogen atoms plus the nitrogen plus 1 more hydrogen plus 12 times 2 plus 3 hydrogen plus 16, altogether 151. Similarly, if you look at the MR of 4-nitrophenol, which we will be requiring in the subsequent part of the calculation, so it is 17 plus 6 times 12, 72, plus 4 hydrogen atoms plus 1 nitrogen atom plus 2 oxygen, adding up to 139. The question also told us that the percentage yield is only 40. Therefore, the number of moles of 4-nitrophenol will be so this is only 40%. Therefore, in order to make it 100%, we will multiply this by 100 over 40, and putting that into the calculator we get 0.08278. That's the number of moles of nitrophenol required. Now let's convert that into mass. So therefore, mass of 4-nitrophenol that is number of mole times MR. We already calculated the MR earlier, so 0.08278 times 139 gives 11.51 G. So far we have answered the reagents, the intermediate and mass of nitrophenol. Now we have to describe the process of purification. So if you go back to the question, part B, you will see that paracetamol is a solid. Therefore, to purify this solid, we need to dissolve it in hot solvent, then cool the solvent to crystallize it, filter it, retrieve all the crystals, wash it with a cold solvent. Let us put the fourth side heading, purification. So dissolve the impure solid in, we should only use minimum hot solvent. So minimum hot solvent, then how do you crystallize it? Cool and allow crystallization. Filter the crystals under reduced pressure. Now there might be some crystals sticking on to the original vessel where the crystallization was done. So you need to collect that also. Retrieve all crystals by scratching with a glass rod. The next and the last item is to wash these crystals in cold solvent. So this completes the description. Question 5. A student carries out 2 experiments in the lab based on succinic acid, that is butane dioic acid, CH2COOH twice. Aqueous succinic acid can be neutralized by the aqueous sodium hydroxide NaOH as per the equation CH2COOH twice plus 2 NaOH gives CH2COONA twice plus 2H2O. Please note that 2 moles of sodium hydroxide react with 1 mole of succinic acid because succinic acid is diprotic and 2 moles of water are formed. This reaction can be used to determine the value for the enthalpy change of neutralization. The student follows this method. Add 50 cubic centimeters of 0.4 moles per dm cubed succinic acid to a polystyrene cup. Measure out 50 cubic centimeters of 1 mole per dm cubed sodium hydroxide, which is in excess. Measure the temperature of both the solutions. Add NaOH aqueous to the aqueous succinic acid in the polystyrene cup, stir the mixture and record the maximum temperature. The table showing the initial temperature of both the solutions and the maximum temperature is given. Calculate a value for the enthalpy change of neutralization in kJ per mole. Assume that the density of all solutions and the specific heat capacity C of the reaction mixture are the same as for water. Let us remember that the definition for the enthalpy of neutralization is the enthalpy change when an acid and a base react to form exactly 1 mole of water under standard conditions. The correct approach for this question is identify which is the limiting reagent for this question. The question has already told us that NaOH is in excess, therefore succinic acid is the limiting reagent. So based on the volume as well as the concentration of succinic acid, we can calculate the number of moles of succinic acid used up in this reaction. And from there, we can calculate the number of moles of water formed. Then we calculate the enthalpy change for the reaction using the information provided here, including the delta T, that is change in temperature. If we divide that quantum of energy by the number of moles of water formed, we will be getting the enthalpy change of neutralization. So that should be our strategy. So let's start by writing Q is equal to mc delta T, that is mass of the solution. So we have been told that the mass of the solution is the same as that of water because the density is the same. So 50 cubic centimeters plus 50 cubic centimeters is 100 cubic centimeters equal to 100 grams times C is 4.18 for water times the delta T was 26.5 minus 21.5, okay, and that is equal to 100 times 4.18 times 5. That gives us a Q of 2090 joules, which is equal to 2.09 kJ. Now we have to calculate the number of moles of the acid CH2COOH twice number of moles equals its volume times its concentration. So 0.05 times 0.4 moles is equal to 0.02 moles. Since the acid is the limiting reagent, it will dictate the number of moles of water formed. You can see from the reaction that 1 mole of the acid produces 2 moles of water, and therefore these many moles of the acid will produce 2 times 0.02 is equal to 0.04 moles. So we got all the information we need to calculate the neutralization enthalpy. So we can say therefore delta H NuUT is equal to 2.09 division 0.04 moles is equal to 52.25, and we need to write this as negative because it's an exothermic reaction, minus 52.25. That's it. Part B. Succinic acid is esterified by ethanol C2H5OH in the presence of an acid catalyst to form an equilibrium mixture. The equilibrium constant Kc for this equilibrium can be calculated using the amounts in moles of the components in the equilibrium mixture using expression 5.1. Kc is equal to, so this is all given in moles instead of in molar concentrations. A student carries out an experiment to determine the value of Kc for this equilibrium. The student mixes together 0.05 moles of succinic acid and 0.15 mole of ethanol with a small amount of an acid catalyst. The mixture is allowed to reach equilibrium. The student determines that 0.02 moles of succinic acid are present in the equilibrium mixture. Question: which technique could be used to determine the equilibrium amount of succinic acid? Titration can be used to determine both the number of moles as well as the concentration of succinic acid. Write the equation for the equilibrium reaction that takes place. You can construct the equation for the equilibrium reaction from the expression for Kc because this refers to the product of the reactants and this refers to the product of the products, and they will be in molar concentrations or molar numbers. So we can write CH2COOH twice plus 2 C2H5OH is in equilibrium. CH2, COO, C2H5 twice plus 2H2O. Next question. Draw the skeletal formula of the ester present in the equilibrium mixture. First, let us draw the structural formula of the ester and then convert that into skeletal formula so that you will know what's going on. So the succinic acid part is CH2, CH2, C double bond O, OH, and here C double bond O, OH, and we have got C2H5 OH here and another unit of C2H5 OH. During the esterification reaction, the hydrogen atom of ethanol and the OH group of the acid move away as one molecule of water. So here also the hydrogen atom of the ethanol and this OH group of the acid go away as water, and therefore the remaining part is, we can now link this as the ester link. Let us now convert this into skeletal formula. 1, 2, 3, 4. This is double bond O here, double bond O here, O. This is CH2 and then CH3, and then here O here, CH2, CH3, and we can now remove these things. Hope this is clear to you. Part 4. Kc is the equilibrium constant in terms of equilibrium concentrations. Why can expression 5.1 be used to calculate Kc for this equilibrium? So the question is focusing on why are we writing Kc expression in moles instead of concentrations? Since number of moles divided by volume is equal to concentration, you can see that in each of these terms the volume as the denominator will cancel out. So we could write volume cancels out in this expression for Kc. Part 5. Calculate the value of Kc for this reaction. Show your working. So let's quickly jot down acid plus ethanol react to give ester plus water. In this, 1 mole of the acid reacts with 2 moles of ethanol to give 1 mole of the ester and 2 moles of water. So at the starting point and at equilibrium, let's find out the number of moles. Okay, so starting point acid was 0.05 moles and ethanol was 0.15 moles. Okay, now at equilibrium the acid was 0.02 moles. That means the quantity reacted is 0.03 moles. Obviously, the number of moles of ester formed will be 0.03 moles and water will be 0.06 and ethanol reacted is 0.06, and therefore ethanol at equilibrium will be the difference between 0.15 and 0.06, 0.09 moles. Cool. So we have all the information that we need for calculating Kc. So Kc is equal to, in the numerator we have 0.03 times 0.06 square divided by 0.02 multiplied by 0.09 square, and that gives us from the calculator 2/3, which is in decimals 0.667. Question 6. This question is about organic reactions. Compound A is formed when ethanol is mixed with OH minus aqueous ions, which act as a catalyst. The balanced equation is shown in reaction 6.1 below. Give the systematic name for compound A. There are 4 carbons here, and therefore it is a butane derivative. And there is this aldehyde group and the hydroxyl group. And now, the aldehyde group is a higher priority group in naming conventions as per IUPAC over the alcoholic group. So therefore, this will form the suffix. So we need to write butane with suffix aldehyde. So we write butanol. And then 1, 2, 3, the third carbon atom has got the hydroxy group. So we write 3-hydroxy butanol. What type of reaction has taken place? So in this reaction you can see there is only one product formed, there is no other product formed. Therefore, it's an addition reaction. Part 3. Reaction 6.1 takes place in 2 steps. OH minus ions act as a catalyst. In step 1, ethanol reacts with OH minus ions to set up an acid-base equilibrium. In step 2, compound A is formed. Complete the equilibrium for step 1 and label the conjugate acid-base pairs as A1, B1, A2, B2. So if this sets up an acid-base equilibrium, one of the 2 species should be losing one proton and the other one should be gaining it. So obviously the OH minus group must be the proton gainer, and therefore let's call this as B1. Okay, once it has gained one proton, it will become what? H2O. So in an equilibrium, it can also go in the reverse manner and lose one hydrogen. Therefore, let's call this as A1, which is the A1 and B1 conjugate pair. Now here, CH3CHO is the proton loser, therefore it should be the other acids. And once it loses one proton, it will be CH3CO with a minus sign, and it can accept one proton now, therefore it becomes the B2. Suggest the equation for step 2. We already know that it is an addition reaction and 2 molecules of ethanol react together in presence of OH minus, which is acting as a catalyst to form the compound A. Therefore, after the reaction, this OH minus should be reformed. Hence, whatever is formed here as an intermediate, these 2 together should react with one more molecule of CH3CHO to form the compound A and OH. So let's write that. So CH3CO minus plus H2O plus CH3CHO should produce CH3, CHOH, CH2, CHO plus the OH minus. Part 4. A similar reaction takes place when propanol CH3 twice CO is mixed with OH minus aqueous ions. Draw the structure of the organic product of this reaction. Let us try to write out the equation in the same way as ethanol. So propanol has this structure, double bond O here, plus one more of that, in presence of hydroxy group, it should form. So you can see that the carbonyl group changes to the OH group. Therefore, CH3, COH, CH3 here, then CH here, and then we have got the carbonyl group and CH3 here. Part B. Many organic reactions use electrophiles as reagents. Explain the role of electrophiles in organic chemistry. Your answer should include one reaction of an aliphatic compound and one reaction of an aromatic compound, including relevant mechanisms. This 6-mark question actually gives an opportunity to demonstrate your knowledge about electrophilic addition and substitution reactions, formation of major and minor products, showing curly arrows, etc. Let us start by writing the standard definition for electrophiles. An electrophile is an electron pair acceptor. So that's the standard definition. Let us write one example for aliphatic compounds. Example can be electrophilic addition of alkenes by a hydrogen halide, let's say HBr, to form haloalkanes. You could write a simple addition reaction without any major or minor products, but you get more marks when you demonstrate your knowledge about major and minor products and label them and the reasons for the major product also. So let's start with writing CH here, okay, double bond C, CH3. This will give you an opportunity to show major and minor products. So this is 2-methyl prop 1-ene. So we can write the name also, 2-methyl prop 1-ene. Okay. Let us write the HBr here. The Br already has got a dipole on it with a delta negative charge because of its higher electron negativity. And this creates a delta positive charge on the hydrogen. Furthermore, the presence of the electron dense double bond creates further polarity on the hydrogen. Therefore, draw a curly arrow from the double bond to the hydrogen. This pushes off the bonding pair of electrons to bromine, which therefore breaks off heterolytically with both electrons. This creates two intermediates, one of which is CH3 here, C with a carbocation, and then CCH3 here, and the Br here with a minus charge and lone pair of electrons. Now it is attacking this carbocation, and further it gives this is the major product because the carbocation formed here, this intermediate is more stable because it has got least hydrogen atoms attached to it, or you could say it's the most substituted carbon atom here. The other intermediate formed is CH, H, C, CH3, CH3, hydrogen gets attached here, and the carbocation is this one now, and the bromine with the lone pair and negative charge attacks this one. This forms the minor product CH, Br here, we can write here minor product. As an example for an electrophilic reaction on an aromatic compound, we can show electrophilic substitution. As an example, nitration of benzene. So let's write the side heading here. aromatic compounds. The example we are going to write is electrophilic substitution nitration of benzene. Nitration of benzene is carried out by reacting with nitric acid in presence of sulfuric acid, which acts as a catalyst. Firstly, we have to write the equation for the generation of the electrophile. So that is HNO3 plus H2SO4 gives NO2 positive, which is the electrophile, plus HSO4 negative plus H2O. Let us now draw the benzene ring and the NO2. The positively charged NO2 is nearby. The high electron dense pi ring of benzene attracts the electrophile. This creates a bond for NO2, but the pi ring is now broken, so we need to show it with a positive charge. Okay, so we can say NO2 here, and there is a hydrogen atom already sticking on there. Now we should show a curly arrow for the bonding pair of hydrogen getting transferred into the pi ring of the benzene. This results in nitrobenzene and a proton. This proton now helps regenerate the sulfuric acid catalyst. So HSO4 minus plus H positive regenerates H2SO4. Done. We can also write here catalyst reformed. Well, that's the end of the question paper. Hope this was helpful to you and you enjoyed it. If you have any questions, please post it under the video and I shall try to answer them without delay. Until the next walkthrough video, wish you well and thank you very much.